Okay. We're going to start off by looking at some naming off of the old exam. As I mentioned last time we did a review, feel free to interrupt me at any time if you've got questions. So this is to benefit you. I don't have to do this, but I think it helps you all to go through and see some of this. Okay, our first one here, for IU says you can use IUPAC naming or you can give common names. So I gave you the choice this time, and that's what I do in organic too. I usually give you a choice every time. You can use either the common name or the IUPAC. Our first one here, we had learned how to name these benzene rings. Benzene was the parent name, with the one exception, and the one exception was when we had a carboxylic acid on the ring, and that's here in the second one. Benzene is the parent name. We have two substituents here. We have an amino group, and we have an ethoxy group coming off. Your substituents go out in front in alphabetical order, so amino is going to come first. I need to tell the position of these. Now, it's the same either way. If I number, it is 1, 2, 3, or it is 1, 2, 3. So it's a tie in numbering. The substituents are on the 1 and the 3 position. When we have a tie, and only when we have a tie, you give the smaller number to the one that comes first alphabetically. So we give the smaller number to the amino group. It gets the 1 position. So this is a 1 amino, 3, this is an ethoxy group, 3 ethoxy benzene. Now that's the IUPAC name. You can also give this a common name. Common, we talked about with the amine on there, that this is called aniline. We still have the ethoxy coming off of the aniline. And that ethoxy is meta to the amino. So we have, here would be ortho to the amino group, meta, and then para. So it's in the meta position. So we simply can put an M, or you can write out meta if you want to. Meta ethoxy aniline is the common name. So you're welcome to give either one.
Dr. Shelby, would it be incorrect to just say meta amino ethoxy instead of putting the numbers for the IUPAC name? Is it wrong to mix the two?
Yeah, well, technically it is. You choose either IUPAC or common nomenclature. You don't combine common and IUPAC. So if I were grading it, I wouldn't count it wrong if you did that. But you stay consistent. You either use IUPAC or you use common. So
how come you can't, in the common, you can't put like a 3 ethoxy?
You can, but common, with these di-substituted, they use the ortho, meta, and para. That was just the common.
Okay, so if I were to put that, would you count it wrong?
Oh, no, no. If you put 3,
so
I'm not going to count.
Here, but, okay.
Yeah, I'm not going to count it wrong if you put the 3 there. No. Like I said, you typically don't mix them, but, if you did, I'm not going to count it wrong. Okay, in our next one here, so with our benzene rings, we always use benzene as the parent name with one exception, and that's when we had a carboxylic acid on the ring. When we had a carboxylic acid directly on the ring, that was called a benzoic acid. And that was our parent name. Now, since the benzoic acid, since we're using the oic acid there, using the carboxylic acid as part of the parent, this has to be the number 1 position on the ring. because it's part of my parent. We're not here, we're not trying to get the smallest set of numbers possible because I've got to use that as my, it says it's part of my parent name, I've got to be using that. That's my one, has to be my one position because it's part of the parent. It's like back here, you know, like with the aniline, that nitrogen was the one position because it's part of, it is part of the parent. Aniline includes that nitrogen, so that has to be the one position, like there. Okay, so we number around to get the smallest numbers possible. Our substituents go out in the front in alphabetical order. So this is a 4-bromo, 3-chloro benzoic acid. There is not any other common nomenclature for that. You can't use ortho, meta, and para here because I have 3 substituents. Ortho, meta, and para are only for 2 substituents. If I had only had 2 substituents, say I only had the chloro group, then yes, I can call it meta-chlorobenzoic acid. That's fine. But when we have 3, you can't use ortho, meta, and para. Questions? Now, in the next question here, I have given you the name and asked you to draw the structure. So we're going the other direction. And I threw some common names at you. So you do have to know those common names I asked you to learn. First one here is orthonitrotoluene. Toluene, if you recall, is a benzene ring with a methyl group. That is toluene. We have a nitro group in the ortho position. Ortho is the positions next to the methyl. The next one out are meta. There's your meta and there's your para. So we're going to have a nitro in one of these 2 ortho positions. Does not matter which one you put it in. It's the same thing. Just flipped over. Nitro is in O2. So there we go. Questions? The next one is paraxylene or p-xylene. And we've actually seen that one in lab last semester. We used it, that's the one we used as a chaser solvent in one of the labs. And this has 2 methyl groups, and para would be in the 1,4 opposite sides, 1,4 positions. So that is paraxylene or p-xylene. Okay, any questions on any of the nomenclature? Our next one, we have a mechanism question. So giving you the full reaction and just asking for you to draw me the mechanism on how the starting materials become the products. Okay, first step of the mechanism is a Lewis acid-base reaction. We have our Lewis acid catalyst in there along with chlorine. This is our Lewis acid. So the chlorine has to be the Lewis base. And the base is going to give a pair of electrons to the acid. There's a large partial positive charge on that iron. So it's wanting some electron density. It's only got 6 electrons, and the 6 that it's got, the chlorines are pulling them away. So So we can get another pair and get to 8 electrons and get the pair from our chlorine molecule. Follow your arrow there to get your charges. Initial tail becomes more positive by charge, so that chlorine has a full plus charge. Final head becomes more negative by charge. That iron now has a full negative charge on it. Chlorine, being an electronegative atom, does not like to having that plus charge on it, so this is going to break apart. And we can get rid of that plus charge if we take a pair of electrons out of the chlorine-chlorine bond up onto that chlorine atom. Broken apart. So this chlorine now, initial tail becomes more positive charge, so that chlorine has a full plus charge. Final head becomes more negative by charge, negative positives cancels out, that chlorine is now neutral. Now, it's our chlorine cation that is our electrophile. That is what's going to react with our benzene ring. Redraw it here so I've got some room. So we're going to take a pair of electrons out of the benzene ring and add to that electrophile. So one of those two carbons is going to get the chlorine, one's going to get the plus charge. And in this case, it does not matter since there's no substituents already on the ring. We did talk about directing abilities of different substituents. If you had something on there, it would tell the next one where to go. But there's nothing on there, so it doesn't matter which one is which. So I'm going to stick the chlorine on here and leave the plus charge there. Now, we have went from an aromatic ring to a non-aromatic ring. We want to get our aromatic ring back because aromatic is so stable. We also need to get our catalyst back. This was a Lewis acid catalyst. Catalyst is not consumed in the reaction. When the reaction's finished, I should have the same catalyst back. Right now, it looks like this, if you recall. Yeah, I already erased it, but it looks like this. So we're going to take the chlorine off, and we're going to come and grab the hydrogen where we just put the electrophile. The carbon that we just put the electrophile on, we need to get rid of that hydrogen. So that chlorine comes off, grabs the hydrogen, you make HCl. That carbon-chlorine bond kicks its electrons in toward the plus charge. That gives us our product, and we have made HCl as a byproduct. And we've also got our Lewis acid catalyst back. But there's our product. So there is the full mechanism showing all the curved arrows on how to get there. Questions? Okay, let's look at some reactions now. First reaction here, this says give the major product or products for each reaction. Our first one here is a 3-step reaction. Got 3 sets of reagents here, so just take them one step at a time. First step, we are adding in MBS and light Solvent may or may not be shown. If the solvent is shown, it's tetrachloromethane is the solvent. So that may or may not be shown. Just don't get confused with if it is shown. That's always the solvent for MBS. So MBS is going to brominate, and if you recall, it only brominates allylic and benzylic positions only. Benzylic is the carbon next to the benzene ring. So, our product after the first step is we have brominated that benzylic position. There's only one equivalent of MBS in there, so I only put one on. If you use two equivalents, we would have had two bromines on the benzylic position. If I use three equivalents, we only have two benzylic bromines in the benzylic position. That's all the hydrogens that I have, benzylic hydrogens that I have. There's only two, that's all I can put on. If you're doing a substitution, this is a free radical substitution on the benzylic position. So two is the most I can get on there. Now, so that's our product at first step. Second step, we're reacting with a strong base. This is a strong base. And you also have heat. We have a secondary alkyl halide. Secondary alkyl halide with a strong base will do E2 elimination. So we're going to grab a beta hydrogen. Alpha is where the hydrogen is. Beta is the next one out. So we're going to grab one of those beta hydrogens off the methyl group there. Just an E2. Electrons kick in to form the double bond and kick the bromine off, so we make an alkene. There's our alkene. Now we did review that, doing reactions on the benzene side chain, I called it. We reviewed the E2, so that's fair game. Anything I review is fair game. And so we did an example. I think I had a couple more carbons out through there, but almost the exact same one I did in class. Now, so that's taking care of the second step. We've made that alkene. Third step, we're reacting with bromine, and we have a Lewis acid catalyst present. That Lewis acid catalyst tells us that we're going to do an electrophilic aromatic substitution onto the benzene ring, onto that aromatic ring. So we know, I'm not going to go through all that mechanism, just same as what we did here just a moment ago in the previous question. Except we had chlorine, here we got bromine, so we know this is going to go and make a bromine cation, and that's what's going to react, and it's going to go onto the ring. The group that is already present on the ring will direct the bromine as to where to go. This is an ortho-pair director. Your carbons, your alkyl groups, phenyl groups, even an alkene group, any of those groups are ortho-pair directors. So we talked about all these different directing abilities. It was easy to tell the difference in most of them. So the meta-directors, you only look at the atom directly attached to the ring. So if the atom attached to the ring had a positive charge or a large partial positive charge, it was a meta-director. If the atom had lone pairs of electrons, it was an ortho-pair director on the atom directly attached to the ring. The only exception to that, so all your ortho-pair directors have lone pairs on the atom directly attached to the ring, except for the alkyl groups, phenyl groups, and like an alkene, a vanillic group or something like that. any of those carbon groups. That was the only exception. So this is an ortho-para director. So it's going to tell the bromine to go ortho and para. You will get a mixture of both. There's nothing we can do about that. I don't know exactly which one will be the major, so I'm not going to have you pick. If it's an ortho-para director, tell me both of them. So we're going to get the ortho, and we will also get para. You can just draw me one and say plus the other. That's perfectly fine, or you can draw them both out if you want to. I don't care either way, but I want to see both. I don't know which one is going to be the major until we go in the lab and actually do the reaction. Statistically, ortho should be the major because there's 2 ortho positions and only 1 para position. But ortho, these are groups are getting kind of close to one another, so sometimes steric plays a role. And if sterics play a role, sterics are going to tell you that it wants to go para, get as far away from each other as possible. So, you never know until you actually go in the lab. You can make some educated guesses, but you don't know in the lab until you go in the lab and do the reaction as to which one would be major. So I'm not going to have you pick on that. If it's an ortho-para director, just tell me you get both. Ortho and the para. Any questions on that one? Let's take a look at our next one. Oh, by the way, before I erase all of this, what if, instead of bromine and the Lewis acid catalyst, what if I had just had bromine? No Lewis acid. Okay, where's it going to go? What's it going to do?
It's going to brominate that double bond.
Yeah, you're going to do an addition across the double bond. We did addition reactions. So the examples I gave in class was we did HBr. You added HBr across the double bond. But we know we can also do addition with bromine. So the bromine is going to add across the double bond. One carbon gets one bromine, the other carbon of the double bond gets the other bromine. Just added across the double bond. It was just an addition reaction. That's the reaction on the carbon side chain. So you have to have the Lewis acid catalyst to get it onto the ring. There are a couple exceptions that we discussed on that. The only time you can get it without a Lewis acid catalyst, you have to have the strongest electron donating groups. So you need like an alcohol or an amine group. It's the only time you can get by without a Lewis acid. All the rest of the times you have to have a Lewis acid if you want to put it on the aromatic ring. Okay, just a little side note there. So that was another reaction type of reaction that we had discussed, so I just wanted to point that out. Take a look here at our next one. This is a really good question. I have seen questions like this one before on things like DATs or MCATs or that ACS exam, that type of stuff. This is the type of deal that you often get. So here, this is seeing if you really understand what's happening. We have chlorine and the Lewis acid catalyst. We know we're going to put a chlorine atom on the benzene ring. You're going to do an electrophilic aromatic substitution on the benzene ring. But uh-oh, we got 2 benzene rings. We have to make a decision on which ring we're going to go to. How do we decide this? How do you decide which ring to put it on?
A greater number of substituents.
Nope.
Stronger activating.
The stronger activating group. We've got activating groups, we've got deactivating groups. What does activating mean? Activating means that group is making that ring more reactive than a normal plain benzene. A deactivating group is you're deactivating the ring, you're making it less reactive than a plain benzene. So this one has a moderately activating group on here. That ring is more activated than this one. This first ring has got a methoxy and it's got a phenyl group coming off. The methoxy is a moderately activating. The phenyl group is weakly activating. So you got moderately and weakly, but this wins out. It's the stronger activating group. That wins. If we were to just look at the other ring, the only thing it has on it has a phenyl coming off. Phenyl is weakly activating. So of the two, this is the more active ring. It has a moderately activating group. That's the more activated ring. This is the ring we're going to add to. And the methoxy wins. The methoxy beats the phenyl. The methoxy wins here. So we want to go ortho or para to that methoxy. Here is ortho to the methoxy, here is meta, and here is para. I can't go para because there's already a substituent in the para position, so the only option is to go ortho. So that chlorine is going to go ortho to the methoxy group. Doesn't matter which side you put, it's the same thing. Does not matter which ortho you go to here. The molecule is symmetrical, so it doesn't matter. So we have done an electrophilic aromatic substitution. We have halogenated that ring. Now, next step. What are we going to do here? What kind of reaction is this?
Benzene.
This is the benzene that we were talking about this morning and at the end of class on Wednesday. We have the very, very strong base. You have to have an extremely strong base to be able to do the benzene. And we have our phenyl halide. So this is going to pull off a beta hydrogen. I have 2 beta positions, but beta alpha is where the halogen is. That's our leaving group. We got beta here and beta here. But this one doesn't have a hydrogen, so you got to go to that one. So the base comes and grabs. I'll go ahead and go through the mechanism of this because we're just covering it this morning, so we haven't seen it that much. So I'll go ahead and go through the mechanism. So we make the anion. Those electrons are then going to kick in to form the triple bond and kick the chlorine off. We make the benzene. There's the benzene. You have the triple bond. Now we're going to take our nucleophile and add. NH2 minus is our nucleophile. That nucleophile is going to add to one of the 2 ends of the triple bond. You have to decide which end it's going to go to. We talked about that this morning. This is the regiochemistry. We're going to add to this end of the triple bond because that throws those electrons toward the oxygen, toward that side with the oxygen so that that oxygen can pull inductively through space, got the inductive effect through space, that can stabilize that negative charge. You want that negative charge closer to that oxygen, to that substituent. Now, to finish this off, this grabs a proton from the solvent, and that gives us our final product. So that amino group wound up going meta to the methoxy. And that's what we saw there this morning. The chlorine that we started with was ortho to the methoxy. They were ortho to each other, and we wound up being meta to each other. So there's the correct regiochemistry. There's where the amine winds up. Questions? Yes?
Will there always be an oxygen that we can look
No,
at for?
no, you can have other things out there. We can have another nitrogen out there. You want something that can pull electrons, and you're going to want to go toward that group. Even a methyl group. A methyl is very slightly electron. It can be electron donating. So, you know, you're looking for something that can pull electrons. Well, methyl it's actually electron donating. That wouldn't be a good choice. You like something that's more electronegative, something that's electronegative out there.
Will it always follow the ortho, meta, 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 para?
Yeah. You always want to get that negative charge right here. You always want it as close to the substituent as what we can get. When we want it going that direction, not the other. See, I could have added this way, and then it's closer to the phenyl substituent. But we want it closer to that oxygen because that oxygen is very electronegative. And so it can pull you got a good strong inductive effect there. So really you want a good electronegative atom out there, and then you want that negative charge as close to it as possible. Okay, other questions? Okay, it says we have an excess of potassium permanganate. This is oxidation of the benzoic position. We oxidize those side chains. So it's going to oxidize the benzoic carbons. There's a benzoic. And here is a benzoic. We have two benzoic. It will cleave off anything out past that. And both of those two benzoic carbons become a carboxylic acid group. There's our product. That's it. So we have oxidized the benzoic carbons to carboxylic acids. Cleave off anything out past it. It just looked scary because it was a big old molecule, but we oxidized any of the benzoic carbons, only benzoic carbons. Questions? Okay, our next one here. We have an acyl chloride in the first step, and we have a Lewis acid catalyst. So we know that that acyl chloride, as that chloride is going to give electrons to the aluminum, and then it winds up breaking apart. And so all of this is going to wind up giving us an acyl cation. I'm not going to go through all that. It winds up going to an acyl cation. So you give electrons from chlorine, and you break it apart. You get rid of the plus charge on the chlorine. You're left with an acyl cation. The nice thing about acyl cations is you don't have to worry about cation rearrangement. They will not rearrange because they're very stable. They have resonance. You have resonance with the lone pair on the oxygen. This one would also have resonance into the phenyl ring. So it's a very stable cation. It is not going to rearrange. Your acyl cations will never rearrange. Now, that is our electrophile. That's what's going to add to the aromatic ring. We'll get our electrophilic aromatic substitution. It's going to go on to that ring, but we got to decide where is it going to go. That's the important part. Where are we going to put that? Okay, there's a lot of stuff already on there. Let's see what we've got. Here, let's get a different color here. Here we have an alkyl group. Alkyl groups are weakly activating. It's an ortho pair director, weakly activating. Over here, atom attached directly to the ring. It's also an alkyl group, weakly activating. Up here at the top, we have an oxygen. It's an ether. These are moderately activating. That is a moderately activating group. The moderately activating group wins out. That's the most activating group that we have. So that oxygen wins. It says, I will do the directing. These alkyl groups have no say in it. They're not strong enough. Your most activating group wins out. It says, I want you to go ortho or para to me. So to the oxygen, here are the ortho positions to the oxygen. These are meta to the oxygen, and this is para to the oxygen. That moderately activating group, that is an ortho para director. We're going to go with the ortho or para positions. And we only have one option here, because this ortho position has already got a substituent, and the para position already has a substituent. And so the only place we can go is this top ortho position up here. That's the only one that doesn't have a substituent on it. So that's where that acyl group is going to go. So I'm not going to go through the full mechanism. It's the same as what we've been doing. We do an electrophilic aromatic substitution. You have put the acyl group, substituted the acyl group on into that ortho position. There's our product after the first step, after we've done the electrophilic aromatic substitution. It goes to that position. That's the major product. Now, second step, this is the Clemence reduction. Clemence reduction reduces aldehydes and ketones to a, reduces it all the way down to an alkane. Let's see what we have. We do have a carbonyl here, but that's a carboxylic acid, so we can't do that. Here we have a carbonyl, and that's a ketone. It will reduce that. It does aldehydes and ketones only. So it's going to reduce that ketone down to an alkyl group. be an alkyl group. Let me just show it here, I'll draw it. That is going to be a CH2 group right there. That carbonyl, the ketone, that ketone gets reduced down to a CH2. Questions? So that was the Clemence reduction. We also talked about Wolff-Kishner reduction, does the same thing. But we really like the Clemence here because not that important, but you know, if I were to ask for reagents, I wouldn't be picky on it. They're pretty interchangeable. But we like the Clemence here because it's under acidic conditions and I have a carboxylic acid. The Wolff-Kishner is under basic conditions, so you don't want a base around with a carboxylic acid group in there. So, you know, we like the Clemence in this particular case. Okay, our next one here. Oh, wow. That's scary looking. 4-step reaction. Let's just take them one step at a time. Don't just try to jump to the product. You make mistakes. Write them out if you need to. I really recommend you writing out each step. At least give me the product from each step. You don't have to write all the mechanism. At least give me the product from each step. So that way, if you mess up somewhere along the way, at least give some partial credit. Okay, so first step, we have bromine, Lewis acid catalyst. So with that Lewis acid catalyst, that's going to break this apart and give a bromine cation. So we're going to do an electrophilic aromatic substitution that will put a bromine onto the ring. So after the first step, this is our product. We made bromobenzene. We put a bromine onto the ring. We only put one on because there's only one equivalent of bromine there. That other bromine, it wound up grabbing the hydrogen. So we make HBr as a byproduct because it grabbed the hydrogen off. Okay. Now, second step, we are reacting with nitric acid and sulfuric acid. This is doing a nitration. We're putting a nitro group onto the ring. The group that's already on there tells the next group where to go. The bromine that's already on there, that is an orthopara director. Because it's got lone pairs. Anything that's got lone pairs on it is an orthopara director. By the way, even if I throw something at you that wasn't in our list, anything with a lone pair, if it's directly attached to the ring, that's an orthopara director. Okay, so we're going to go ortho or para to the bromine. Here is ortho, meta, and there's para. So we'll get a mixture of both ortho and para. We're putting a nitro group on the ortho and para position. I will draw the ortho here. Now I want both. Here is the ortho. You can just draw one and say plus the other. That is perfectly fine. Or you can draw both of them out. So you get the ortho, you get a bad mixture of ortho and para. So we put a nitro group on. That's just another electrophilic aromatic substitution. Third step. What in the world is that? This is kind of a, I didn't realize I had that. What in the world did I write as the, that's kind of a bad question. Oh wow, this one's going to give a bad mixture of things. This I didn't even think about it when I wrote this out. And even when I wrote my answers, I wasn't thinking. With the nitro group on there, we have a nitro. We have a phenyl halide with a nitro that likes to do SN1. I said SN1. Duh. SNAR. So because of the nitro in the ortho and para positions, we like to do SNAR. But I have an alkyl lithium. See, there's an alkyl lithium. That's a very, 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 very strong base. Alkyl lithium like to do benzene. So this one could do either the SNAR or do a benzene. Now the problem with that is you get different products. Because this one here is ortho. If we do benzene, we know we're going to get a meta product. If we do SNAR, you're going to get an ortho product. So I get a really bad mixture. That was not a good reaction to really have. So if you're doing SNAR, you substitute right where the bromine is. You're putting the alkyl group on. You would also have the para. You have the ortho and the para if you're doing SNAR, and that's what I had on the answer key. But if you're doing benzene, you wind up with the meta. So we're actually going to probably get all of those. You'll get benzene and some SNAR as well. So that's a really a bad question.
So we won't have a question quite like that.
No, I wouldn't have it. I shouldn't have had. That was just a bad option there. I shouldn't have done an alkyl lithium there. I shouldn't have had where you could choose benzene or SNAR. Let's just change it. Let's do, here, we'll put something else where we don't have an option. Let's do, here, let's change it to this. Let's do this. Now, this will only do SNAR because that's not a strong enough base to do benzene. So this is only SNAR. So that's a much better question. So if you do that, then we can only do SNAR. And so we wind up substituting. Ortho will give ortho, and the para still gives para. SNAR just substitutes straight onto that position. So that's a much better question. I don't want you having a choice between SNAR and a benzene. Okay, any questions on that?
So what is the answer for the both or that one?
We would get both here. You get only ortho and para.
Okay.
Because the ortho one here, see we got a mixture back here, so ortho will give ortho, and that para gives the para one. Other questions? Let's get another one done here. Okay, our first step here we have chlorine, and I was nice and say excess, but chlorine is always an excess because chlorine's a gas. You can't weigh out one equivalent of chlorine or two equivalents. You just have to bubble it through, it being a gas. So you're always, if you're using chlorine, you're always going to have excess. Okay, so chlorine, you notice that there is light there with it. So this is going to do chlorine radicals. This is not going to go onto the ring. If we want the chlorine onto the aromatic ring, you must have a Lewis acid catalyst in there. There is no Lewis acid catalyst, it's light. So this is chlorine with light is going to give chlorine radicals. This is going to go to the benzoic position. This is a benzoic carbon here. So you're going to have to pay attention on the exam as to what else is in there. So this will chlorinate on there. Since you have an excess, it will get every one of the hydrogens, the benzoic hydrogens. Now, if you had a Lewis acid catalyst, then yes, it would go onto the ring. But you have to have a Lewis acid catalyst to put chlorine on the ring. This doesn't have a catalyst. It's just light. That gives radicals. So we have halogenated the benzoic position, the benzoic carbon. Now the second step, we have sulfuric acid and sulfur trioxide. This is going to put a sulfonyl group on to the ring, and we've got to decide where it's going to go. The group's already on there is going to do the directing. So let's see what we have. We have an OH group that is strongly activating. And we have the CCl3 group that is strongly deactivating. The strongly activating group wins. Now, it didn't really matter in this case because they both are going to send it to the same place. But technically, it's the OH group that wins. Strongly activating wins. It's going to do the directing. So it says that is an ortho-para director. So I want you to go ortho or para to me. So here are the ortho positions to the OH. Next one's out or meta. And here is para. Now we already have something in the para position, so I can't go there. So it's got to go in the ortho position. We are putting a sulfonyl group on in the ortho position. So that is SO3H. Don't forget the H. SO3 adds, but that would have a negative charge and you pick up a proton off the acid. So it's SO3H that you're putting on there. If you wanted to draw that out, this is what it looks like. So you have to have the hydrogen on there. That one oxygen picks up the hydrogen. So it's an SO3H group. That's our sulfonyl group. Okay, questions? We've been going almost an hour. Let's take a break. So that will end part one of my